Hey, thanks guys for organizing this. I really did not know that we had such passionate Druid developers here, both in terms of users and committers. I didn't know that Imply actually had an engineering office in Bangalore. So yeah, it's really good to be connected with the community. So great. Um, let me start off on the agenda here, right? So this talk is all about how we at Noon, the social learning platform, uh, have actually built a real-time classroom monitoring system on top of Apache Druid. So before I go into it, right, I just want to outline what we are going to talk about today. We'll start off with a brief introduction about who we are, and what is this live online classroom and what are the challenges that we typically face. We'll get into about what is quality of experience, and then we'll get into the solutioning part of things, right? We'll introduce the problem first and then get into how Druid, we felt as a team, we felt Druid would actually help us solve this problem. And then a little bit of details into how we actually build this system, right? And towards the end, I'll also share, information about how we actually were able to make a business impact with this, right? What kind of business impact we were able to create, and more importantly, the challenges faced and lessons learned along the way that I would like to share with the community. So without much further ado, right? Let's get right in. Who we are, right? So Noon was actually founded in 2013 with a mission to radically change the way students learn. Through a lot of trial and error, right? We have learned that the real problem in learning for students is not so much about lack of content or anything else. It's mostly around boredom. The fact is nobody likes to learn. Nobody likes to study. So that's the real problem that you want to actually solve. And the way we feel we can solve that problem, or partially at least address that problem, is by making learning more social and fun and more light. When I say social, what it means is learning more from your peers and not just from your teachers, right? This is something that we, growing up as kids, we've done. And I felt, when we decided to pivot, this was the direction in which we wanted to go, building social learning applications where the learning process itself becomes a lot more fun and less tedious. So we have over 10 million students who have tried out our app across 5 different countries, and we predominantly operate right now in the Middle East and South Asian markets. We have over 1 million monthly active users, and when a student is active on a day on the platform, we see them spend more than 50 minutes on an average. Moving on, okay, what does this live online classroom actually look like, right? At the core of it looks very similar to what you experience on a Zoom call, right? So there's going to be video, there's going to be audio, and then there's going to be a whiteboard. Right, and you also have a mechanism to chat. What happens on a EdTech platform like Noon, right, is that a vast majority of students' time goes into learning from their classroom, and that time is actually spent inside the live classroom. So the tooling and all the services that you provide inside the classroom, has to be top notch for students to have a really good experience, right? And speaking specifically around, the areas that we will concentrate on this particular session is around the audio and whiteboard, right? You have to listen to hear the teacher, and then you have to follow what the teacher is actually, drawing on the whiteboard. Apart from this, like I said, we are a social company. We've introduced something called breakouts way before Zoom actually had breakouts. So the idea is that after the teacher has taught you a certain concept, say isotopes, he can ask a question. He or she can actually ask a question, and that triggers a breakout. So students get grouped into smaller groups, and then they can talk amongst themselves, they can discuss, and then come up with a collective answer to that particular question, and then present it to the teacher again, right? So there is facilitates a lot of interaction between teachers and also among students, right? And what we've seen during our live classrooms is that there are certain teachers who are extremely popular, and we've seen up to 10K students attending those sessions, right? So moving on, right? What are the major challenges here, right? The two core challenges that we face are around the audio and whiteboard, and the biggest issue is this, right? I can't hear you, sir, ma'am, I can't hear you. So typically, what happens is when a student starts experiencing issues, right, this is how it will play out in a classroom. So the teacher is teaching, and then the kids who actually have issues hearing the teacher's audio are having trouble following the teacher's canvas. They start typing in on the chat saying, hey, I'm having trouble hearing you. I'm having trouble seeing this on the whiteboard. And the moment this, a critical number of students start posting this, right, the teacher will start looking at the chat and he gets distracted. So when the teacher is distracted, it disrupts the whole classroom, right? And the moment this happens, it gets flagged to our operation team or the tech support, the first line of support, right? And the moment they get a call about this, right, they call the developers, and everybody is running around trying to find out what is going on, right? So when we troubleshoot these issues, we found that the voice problem typically emanates from the teacher's network quality not being up to the mark, or the teacher actually having issues with his or her microphones, and then students on their end, they have issues with their network. And in some rare cases, we've also seen ISPs having policies around VoIP that actually comes in and causes all these problems, right? With respect to whiteboard, what we've seen is issues around events being lost because you had a minor blip in your network, and as the teacher was drawing, few strokes got missed out. So instead of seeing a circle, you're now seeing a semicircle, right? And then the CPU usage on the device goes so high that the sketch is not able to catch up, or there is a lag in that, right? And then there are genuine bugs in the whiteboard logic that could also be causing this, right? So these are some of the challenges that we get, and it's really disruptive and breaks the flow for the teacher, and it's extremely cumbersome for the students, right? So we took a step back and said, hey, you know what? Instead of tackling this one at a time, right? Why don't we actually measure our quality of experience in the classroom, right? And then come up with a plan as to how to actually tackle them. So we set out to measuring quality of experience, right? This is the standard Wikipedia definition, right? The measure of delight or annoyance that a customer experiences. So there are two parts to this when you're trying to measure. One is a quantitative part that is largely around metrics like what's your uplink quality like, what is your audio levels, what are your what's your network speed, what is the bit rate, and then there is sort of like a perception factors, like for example you have to run like a survey to get a sense of whether there was a real problem. Run some surveys and then get this subjective factors measured, right? So for this talk, we'll talk about the quantitative measures that we can easily capture as metrics and then measure. So before we go into the further technical aspects, right? Just a very, very brief overview of how our classroom actually works, right? So there is a teacher who is using a desktop application, sorry, a web client, basically a browser, right? A browser app. And then the students typically tend to be on their mobile devices. So we use a third party called Agora, who provides voice and real-time messaging as a service. So we include their SDKs, and the moment you include their SDKs, you can actually call up a few methods on that, and then quickly set up a audio channel and also a messaging channel, right, through which you can actually broadcast both audio stream as well as messages. So the messages are what we use for the classroom. the whiteboards in the classroom, and then the voice is what the teacher uses to talk in the class, right? So this is sort of a very, very high level, overview. And then we started, breaking things down into what kind of metrics that we want to actually measure here, right? And then what are the different dimensions in which we want to measure, and what are the kind of aggregations that we wanted to actually perform on those. So on the metric side, since I said this talk will primarily focus on mostly the audio and whiteboard aspects. We are interested in understanding the uplink and downlink network quality, of the teacher as well as the student. And then we want to understand the packet loss, right? Amount of packet loss happening on both sides. Then we also want to, figure out what is the audio quality like, right? And then the microphone status, right? Whether it's on or off, and then the jitter buffer delay, and then the frozen frame, right? Like we experience on Zoom when you see the voice cracking up at certain points because there are frozen frames in the audio packets. And then we also wanted to capture on the whiteboard side something that we call as a drift, which we'll cover in the subsequent slides as well. And then on the dimensions, just to list out a few, right? We want to know which country, which ISP, basically geographic factors, and then which ISP, what kind of network he is on, a 4G network or on a broadband network, and then users, user ID, and then the classroom ID and things like that, right? In terms of aggregation, we wanted to actually get count, distinct count, average, percentiles, and then standard deviation. These were our sort of like top aggregations that we had actually needed, right? So in terms of system characteristics, right, or like they say, the non-functional requirements of the system, right? What should that look like? One aspect was very, very clear, right? There is a need to do things in real time. So when students experience a problem, goes to teacher and teachers call the ops, you don't want to tell them that, hey, I have a batch job that's actually running and it's going to take 2-3 hours for us to actually crunch this data and then generate a report, right? You want to immediately look at it and say, okay, this is the classroom that you're in, and here are the 5 students who actually have problem, and these 5 students are using this particular mobile service provider, and their bandwidth seems to be not so good today. So that's the problem that's actually happening. So we want to get to this, and we don't want engineers to be in this process at all. We wanted our operations or technical support team to be able to handle this themselves. So real-time ingestion was a big aspect of the requirements that we had. The second aspect was ability to scale horizontally, right? As a startup that's actually adding more users, we knew that we wanted to actually have a system that can actually just scale horizontally by just adding more servers, right? And then because we are dealing with a lot of sessions and user data, high cardinality, ability to handle this was also important for us. The next one is sub-second query latency, right? It was touched upon by Kundan as well in his previous talk. That when people query, right, nobody has patience to wait anymore. So we wanted sub-second latency and then extremely fast aggregation over a larger data set, and then an ability to zoom in and zoom out. And I'll show you an example of what we mean by that, right? And of course, we wanted the system to be available all the time. So with all these factors and both the functional and non-functional requirements, when we evaluated different things, Druid was at the top of mind for us for the following reasons, right? One, it actually supported real-time ingestion from Kafka through those spec files. However long those spec files are, it still made it easier, and it was kind of provided out of the box, right? Without you having to do a lot of work. Then the second aspect was that the architecture of Druid, right? The way it's built, the master nodes, the data nodes, and then the query nodes, right? You can actually scale any of these components independent of each other horizontally, right? So that was something that appealed to us, the distributed architecture of Druid, and then the other thing was the sketches for high cardinality columns, where because sometimes you need exact values and sometimes it's okay to do approximation, right? And that's where Druid did really well. It can give you both exact and approximate aggregations depending on your use cases, right? And then low latency querying. We found that the latency was well within our acceptable range. Then in terms of reducing the data size, right, we looking at the data size overall, we had levers to actually reduce the size of number of raw records through rollups, because in some cases we just prefer to have rolled up data aggregated at a certain time interval. That would just work fine. The other part was fault tolerance built at multiple levels, right? Like if you have an ingestion task, right, you can actually set up replication for it. And by having these replications, I think someone was asking in the previous session as well, right? What if the job dies or something, right? You have replication, and we've tested it out, even though we don't use it in prod, but we've tested it out that you don't really lose data when you kill one of those peons, right? So moving on, right? So into the solutioning part, right? So our first step in building a solution was data collection, right? So we started with how do we collect the data that we need along two major parameters, which are actually around network and audio. So the way it works is the teacher's device and student's device, they have this library embedded in them, which captures or which gets a callback for every 2 seconds. We use WebRTC internally, and WebRTC provides a whole bunch of statistics on your network and audio characteristics, right, that are actually happening right now. So we capture those stats, and then what we do is, instead of sending them immediately to the backend, we actually buffer them and wait for either a terminal event or a certain time interval, and we've chosen 1 minute as the time interval for us. So every 60 seconds or at a terminal event like end of the session or something, this captured information gets pushed out to the server. So NoonGate is our central server that actually receives all these analytics events, and all it does is captures these data points and then just dumps them into a Kafka topic, right? Then the second part, right, of data collection, we talked about audio and getting the base, fundamental network aspects of the user. On the whiteboard side, right, it's a little bit more tricky. So it's important to understand how our whiteboard, sort of works, right? So when you actually draw a line, right, as I have illustrated here in this table, if you have to write A, you need to, draw a slanting line, sort of like there's a forward slash and then there is a backward slash and then a horizontal line, right? So these are the three strokes that actually make this character A. So when teacher actually does this on the whiteboard, what we do is once a stroke is done, it is actually all the XY coordinates along that particular stroke are captured as an array and sent to the channel, and then from there it gets received by all the subscribers on the channel, right, through real-time messaging. So what we did was, along with this array of XY coordinates, we ended up sending something called as a message ID and then a checksum. So the checksum was nothing but the sum of all the message ID up until that point, and the message ID was a monotonously increasing sequence number, right? So using this, what we were able to achieve was the student, when the teacher actually draws a stroke, it gets broadcasted to the student device, and we had an interceptor on the server side that would also get all of this information, and then keeps sending and heartbeat to the student side. So students' devices, right? So it's sort of like a broadcast, right? Everyone subscribing to this heartbeat event. So the moment the student devices receive this heartbeat, the heartbeat actually consists of just the last message ID broadcasted by the teacher, and then the last checksum. So the moment they get this last message ID and the checksum, they can also generate the checksum based on all the events that they have received so far, and they compare the checksum. If the checksums are different, or the last received message ID is different, then you know that you're actually behind. Behind in the sense you're not seeing the same thing that the teacher has actually drawn on the whiteboard. You probably missed out some strokes, right? So this is actually computed, and then we capture this information every 10 seconds, and then aggregate and then sort of buffer this for a duration of 60 seconds, and then flush it to the backend again. So again, it's a noon gate service that receives this and then just dumps it into a Kafka topic. So moving on, right, to the next part. So now you've got all the data that you wanted into your Kafka topics, right? So the next step is to actually take that and push them into Druid, right? So like I said, all our ingestion happens through Kafka. So we have Flink topologies that we started writing to pick up these events from Kafka, just transform them into a format that Druid ingesters can actually take and work with, right? So the data gets sent in batches because you have data coming in every minute, and each data point that comes in has 30 smaller data points inside them, right? So you need to unpack the events, split them, and then format them, and then push it out. So on the real-time ingester in Druid, right, what we've done is, depending on the use cases, certain use cases we have enabled rollups, certain cases no, and then we also have conditional transformations, right? A simple example is that every time you get one of these events, you can actually infer that a user has spent 2 seconds inside the classroom. So those are conditional transformation that you do, which you can actually do at the query time as well. But we have figured out that doing this at ingestion is a lot more cheaper, so that not every query has to do it, right? And then the other thing that we haven't used, but we are really looking forward to, is the lag-based autoscaler, right? Because these ingesters, one of the things that we've noticed is when there is a spike in traffic, there is a certain peak time in the evenings where there's a lot of session happening, right? There tends to be a little bit of lag, and it'll be great if the task can actually sort of auto scale themselves for that. So something that we are looking forward to trying in the in the subsequent quarter. So one of the things that we started noticing was, as we started onboarding this for multiple cases, we realized that there is a pattern here, right? All you're doing with ingestion is you get some data, and then it's in JSON format, and we use protobuf schema we use a protobuf schema and then generate JSON. So it's not binary data, but it's still JSON, but comes from a well-defined schema, right? We have the structured JSON, and all we are doing is parsing data from it, right? And just transforming it. So it sounded like we can easily automate this whole process, right? And then the spec generation, all of it. So what we did was we came up with another configuration, which we call as our internal DSL, which basically has something like this, right? A JSON path that actually says what is your parsing logic, right? And then it also captures what are your dimensions, what are your matrices, and then what kind of aggregation that you want to run on them, right? So with this information, we are also able to capture, what are the topics and then which output topic to produce. So once a developer defines this file, right, or even an analyst defines this file, what we do is we take this particular configuration file, and then we are able to generate jobs out of it for Flink. And then we are also able to take the same file and then generate spec files through a Jenkins job that just takes this, parses all of this, and then constructs your ingestion spec file, and then deploys it on Druid. So the next step, actually, before you ingest, you need to have your schema. So in terms of data model, right, the way we approach this is, you always start from a use case and make sure that this use case, you really understand this use case, right? You've spoken to all your stakeholders, your users, and understand very clearly, right, what you're trying to measure. And once you start from there, right, you can sort of work backwards to identify what are your metrics, what are your dimensions, and then what kind of aggregations that you want to run on them, right? And once you figure out the aggregations that you want to run, the next thing that you want to decide is whether your customers or your users are fine with approximations in those cases, right? Hyperlog or quantile sketches, use any approximation techniques that will actually help you get those results fairly quickly, right? So it's a trade-off between accuracy and speed. So make sure you understand your use cases and you're able to sort of apply this accordingly. The next aspect was the query granularity, right? What level of depth that you want to go for a certain query? Like, do you want data at a second level, or at a hour level, or at a day level, right? So that plays an important role in the size of your in the sheer number of records that you hold in your data source, right? Your tables, and then the partitions, right? What kind of partitioning are you going to use? Then in terms of storage, right? Whether you want to go with S3 for your deep storage, or Hadoop, or whatever that works for you. And then you need to think about retention, because what we have realized is that there are other systems that you can actually use if you want to crunch data for the last 5 years or 10 years, right? Druid is more for at least we have used it for more real time, and look back for a certain period. So you have to define what that period is to keep your data size sort of small. So moving on to the dashboard that we actually built on top of Druid, right? So this is sort of how it actually works, right? So we start off by having what a bird's eye view of at a sort of like a country level, right? So this is how the dashboard looks, where you can actually see here, right, for across these four different countries, the network quality as well as the audio quality, and the moment you sort of find out where they are, then the next step is to so the numbers here actually indicate 1 indicates excellent, 2 indicates good. So we have it's a scale between 1 to 5, and then the next part is actually to sort of dive deep into all the classrooms or sessions that have happened within that particular country. So in this case, you can see for India, what are the number of sessions that have actually happened, and what are the P95 scores for the network quality, and then the audio quality, right? And then once you've got into the session level, country level session view, then you can actually pick up a particular session and then look at what is the overall metrics on that, right? How many students were there, how much time they have spent, what is the P95 audio quality and network quality, and number of chats that were actually sent, all of that, right? And then you can drill deep to find out what actually happened to each of those students within the session, right? So you can go at a session and look at all this individual students, what kind of experience they've had, and if you want to troubleshoot and find out, okay, what happened to this particular student, right? Then you can actually go into much more finer detail and get this level of exact raw data at a 2-second interval, saying, okay, what actually happened at that particular point in time for this student. So a little bit
just
of overview. Yeah.
Sorry. So just a time check. We have like 10 minutes left for the session. So I do want to keep some time for Q&A.
Oh, okay. I'll try and wrap this in the next 5 minutes. Okay. I think I'll try and speed up.
Thanks.
Thanks. So in terms of the cluster topology, right? I think the key thing that I wanted to highlight was, in the interest of time, right? The key thing is this, right? The tiered data nodes. What we observed was that as we had rollups enabled for certain for certain jobs, right? The ones that actually had rollups, they were consuming a lot more memory than the others. So we had to actually tier our data nodes into high memory nodes and then low memory nodes, and then assign tasks accordingly. So putting everything together, right? So this is sort of the overall flow. We have apps that actually have the instrumentation logic, pushes all those events into Kafka, and then from there we have Flink jobs that actually take up these events, and then just converts them into what we call a spec compatible events, which again go into Kafka, and then Druid consumes from there. And through the DSL config file, we are able to generate those specs that can be deployed on Druid for auto ingestion, right? And then we have a dashboard on top of it. So in terms of business impact, right, what were we able to really achieve, right, with this? We were able to quickly identify the bottlenecks and the problems that students were actually facing. The next thing was we were able to, whenever we made an improvement, we were able to validate that this was indeed moving the needle in the right direction or not, right? And through the self-serve tool, we didn't really need the developers to debug everything. It was sort of democratized. Everybody could do this, right? And then the overall, this whole thing actually improved the trust between the support team, the ops, and the developers, right? And finally, the important thing was the student NPS score actually improved with all the improvements that we were able to do in this. So in terms of challenges and the key lessons, right? Again, in the interest of time, the major thing that I wanted to highlight is because we were actually doing, real-time ingestion, one big problem that we had was late arrival of messages. And because of this, even though compaction had actually happened and we had there were segments created, there were new segments being created because of these late arrival messages. And what we ended up doing was, because there is a time frame to how this app is getting used, we were able to find lean times during the day and set up jobs that would actually trigger compactions. So we would actually go back and compact data for a 24-hour window past, like, say, yesterday. So that actually made sure that we were able to stick within the certain number of segments that we had. The other call out is, major thing is it takes time to set up a Druid cluster. It doesn't happen within like a week or two. It just takes time to understand your workload and then configure, tune. It's an iteration. But once we were able to do that, right, once we got it to a certain state, we've never had to go back and touch it. And that is something that I wanted to actually, just call out in terms of challenges and key lessons. So I'll stop here, and, happy to actually take any questions.
Thank you, Karthik. Let me quickly give the unmute permissions. Just a minute. Yep. So anyone should be able to unmute themselves and ask questions.
Hi, Karthik. This is.
Hey, hi, Robin.
Hi, Karthik. Thanks for the wonderful talk. I think that insight about boredom being the main challenge, that's a great insight. My question is around this DSL config file, and we had a similar problem, and we wanted to make this as self-serve. But what we realized was there was a lot of possibility of somebody creating a DSL, defining a DSL, which might lead to, for example, a very high cardinality Druid cube and cause us certain issues, right? Or, a topic which is very high throughput and our Flink cluster might not have been scaled for that, right? So have you built any guardrails on that, and how are you?
Great question, Robin. So definitely these are possible, right? In fact, we knew that we are opening up a can of worms, right? But then as a startup, that's the only way for us to actually go fast. We have to take our chances. If I was at a large enterprise, right, it would have been a big no-no. There'll be a lot of people, talking about it. But here, we felt, this is the way for us to actually learn a culture where people can actually iterate rapidly, and fail fast, right? So, we put in minimal checks and balances is what I would say. But then we've not seen a scenario where people have actually gone and done something really bad. So yeah, yes, definitely there is a risk element opening it up, but the downside of it is somebody has to write these files themselves, right? So nobody wants to do that, right? So if you have a use case and you want to solve it, go all in, right? Opportunity for you. So this is a cultural thing. So we did not solve the problem. The risk is still there. But what we've seen is if you put enough trust and educate people, right, about the guardrails, in a smaller organization, you can actually get away with it. So yeah, not a straight answer to you, Robin, but yeah.
No. I understand, I think. And because I was saying we went through the same problem, but we went to the extent of actually creating an SDLC for it, where we create a first, somebody can create a staging cube alone, right? And the staging cube only takes, for example, only 1% of the actual production data. You can't have more than.
And we have a staging actually. So that is actually happening. So you have to test it on stage and then only deploy it in prod. And we have a process where you have to soak it in the staging environment for 2-3 days and then observe, right? So we do have those minimal guardrails, but it can never be perfect, right? Checks and balances will never be perfect. You will have to learn iteratively. Somebody has to break it, and then you'll realize, oh yeah, I need to plug that now. So yeah. So one of our value proposition is being bold as a company, right? Own it and be bold. So yeah.
Cool. Thank you.
Yeah. I see another question there about reporting done via superset. So this is, we tried superset. Unfortunately, we couldn't make it work because we came across one restriction in superset, which was, it was never able to go below a date range for us. There was a casting problem with the time stamp that we had, which was at millisecond level. And then the Druid superset plugin supported was just at a day level. So we were never able to crack it. We tried it for 2 days and then we gave up, and we used something called Turnilo, which is basically pivot that Imply has, the open source version of it. So Turnilo, there's a company called Allegra, which is actually managing it. So we've used that for the UI. Oh yeah, Srikanth, you're right. It looks like Pivot. It's the open source version of Pivot. It's not the Imply Pivot. So yeah, it's Turnilo. It's like the MySQL story, right? Somebody took a copy of MySQL before before Oracle took it out. So yeah.
Interesting. I didn't know that. Yeah. Sorry, go ahead. Someone had a question.
No, I was just saying, is there any other questions?
No.
If we have time,
yeah, sure, go ahead.
Yeah, I think I'm picking up from the last question I asked, which was about fault tolerance, and then I think we spoke about ingestion tasks or beyond task having replication, and that is how it can be solved, right? But if I'm not wrong, it's more of a discussion. If I'm not wrong, there is a similar scenario that exists for historical tasks as well. As in, so if a historical node goes down, then another historical node, you replace it with another historical node, or the segments are redistributed amongst existing remaining historical nodes, right? During that time, if it has to load data now from the deep storage, and while it is loading data, what happens to the queries? I'm unable to recall. I think we tested it, but I'm unable to recall that. What happens to those queries which might be fired on historical segments which are unavailable right now because a historical node which was hosting them is gone down?
Based on what I can recollect, okay, guys, if I'm off, please keep me honest here, okay? Based on what I recollect, when we did the fault tolerance testing, right, we tested it at on the task there is replication, and then when any commit, any write operation actually happens, right? Druid by design is actually consistent, right? So the writes are actually durable, right? So you don't lose them. So the moment you actually have replication set on your, for all your data sources and your ingestion task, right? When I started randomly killing certain processes and testing it, I didn't see any inconsistency popping out. So that's just my observation. I may be wrong, but I've seen that this multi-layered fault tolerance in Druid, right, on the task level as well as segment, replication, as well as the deep storage that it has, right? I think there is enough fault tolerance built in where you can sort of trust the system unless there is a major catastrophic failure to give you the data that you want. Because I have also not seen, just like what Kundan said earlier, right? I've also not seen cases where we've not seen a single case so far where a student said, I had an issue and we missed that data on Druid, on our system today. Touch wood. So sure. I haven't seen data loss.
Yeah, so if I may pitch in, if you have some replication, say 2, even if one historical goes down, unless like you're killing all of them at the same time, there will be a backup historical. So the broker will send the query for a segment to the other historical in case one historical is down. But if the 2 historicals go down at the same time, I'm not sure of the exact behavior, but it's possible that you may get inconsistent results. There is a mechanism to avoid that to a certain extent. But that's kind of, it may not be well documented.
If I can chip in, I think that the broker would, if it is not able to find the historical or the peon, it would actually respond back saying, fail the query, or it has the option to, you have the option to override it with the configuration, get whatever results you have. I think there is a configuration to allow you to get partial results. By default, I think it fails the query if it does not find all the segments that it requires within the time range.
Okay.
Yeah, I think it must be something like that, because Elasticsearch, for example, allows you to say whether I am interested in partial results or full results alone, right? And you can configure that and you can get those results. I'm hoping most distributed systems would have something similar, and so Druid must have that. Maybe I've just not explored that area.
But then the catch is also this, right? Your availability is defined by the number of replications. So when you say you have to, it's called fault tolerance, right? It's not disaster recovery, right? It's fault tolerance. So you can, accommodate for certain number of failures, right? So you design that your replication factor, everything is, sort of, calculated and set up for that, right? So if all the replication goes down, then yes, you have to assume there's something, something is not going to be right with the results, definitely.